So energy is a cool thing because it gives us freedom. Energy is a replacement for the labor of human beings. That's my favorite definition of it. And it really gives you, we're lazy inherently, and if there's something that will do stuff for us, well, that's great. And it really matters too, because if you look at low energy things like construction, that's not going to work on there. Low energy construction versus high energy construction has a huge difference in quality of life of the laborers. Absolutely huge. I think that's clear. Farming, how many of you grow 100% of the food you and your family consume? I don't. I go to the grocery store. And the reason is because we have high energy farming systems that can do industrialized farming and free us all up to go do what we want. We can choose to spend all of our time getting food, but we don't have to. And that's the freedom that energy gives you. Fetching water is a really serious one in parts of the world today where people spend 4 hours walking to the river, washing clothes, and 4 hours walking back. That's not a great, again, you can choose to want to do that, but a lot of people wouldn't choose that given the choice. And just having a little pump and a pipe to give you fresh water powered by energy is a massive improvement on quality of life. I think you get the point. Traveling to Oregon and 6 weeks on the Oregon Trail could be fun, but anyway, we'll skip that. You kind of get the point. And this can actually be quantified to a degree. And here's an attempt of it. This is the Human Development Index is the UN's attempt at quantifying quality of life. Of course, it's imperfect, but it includes economics and health and education. And this is plotted versus electricity use per capita. And what you see is really astounding. You see two crazy features. A vertical line where a tiny bit more energy vastly improves your life. These are the people who are getting the pump and the pipe, whose lives are completely transformed for the better when they're given that freedom to choose. And there's a lot of these bubbles are proportional to population. So what you see is there's sort of a moral imperative to enable energy access to vast numbers of people. That's increased energy over what we have today. You'll see where this becomes a problem. And then you see United States and Norway, where we're in this total other asymptote, where if we had a little bit more or less energy, we wouldn't really change our lives that much. And you can kind of sense that we're all sort of energy saturated. But so there's room for efficiency and reductions and conservation, but there isn't here. You can't use conservation to boost, to produce billions of watts necessary for that many people. So anyway, so that's the overall thesis. And you can all think of the problems that are coming up. So where do we get our energy today? Here you go. 84% of our energy is in the gray, fossil fuels. Dun, dun, dun. And this is total energy. This isn't just electricity. This is electricity plus transportation, plus building, space heating, plus industrial uses. And then you see you got your wind and solar at 4%, hydro at 7%, and nuclear rolling in at 4% of world energy. So vastly fossil fuel. And now, does anyone work for the fossil fuel industry? It's okay. I'm gonna spend some time trashing fossil fuels. I hope no one cares. We're in Seattle, so you'll probably let me do this. But before I do, I have to sort of say, hey, fossil fuels provided that quality of life for lots of people, including all of us, through the Industrial Revolution. Every sort of big industrial thing you can think of, from the railroad to going to the moon, to the Beatles and the electric guitar and every Katy Perry music video and computer servers, they're all fossil fuel powered, for the most part. And so we're at a point where we kind of have to thank fossil fuels and say, like, okay, fossil fuels, you're better than nothing, but you've got some problems, so we're going to thank you and kick you out. Like, what's that cleaning philosophy? You know, where you like take your stuff and put it in the pile. That's what we have to do with fossil fuels. All right, so what are the problems with fossil fuels? So there's two big ones. The first one isn't the one that's first coming to your mind. It's the one that's a true health emergency in the world that we don't really experience much, which is just air pollution, regular old air pollution. And there's two forms of it. There's 3.8 million people who die per year because they're on that low side of the energy curve. They're going out and bringing wood and dung inside and cooking. They don't have a proper stove. It's making smoke. They're breathing it and they're dying. Early deaths from upper respiratory disease. That's biofuel and dirty fuel. Not good. And then you have the people who have fossil fuel in dense urban areas in India and China. Now you've got 4.2 additional people dying every single year from air pollution. This is your PM 2.5, your SOx, your NOx, all this stuff you've at least heard of. So fossil fuels and biofuels bad because of air pollution, straight up. World Health Organization, not controversial. And then you have the problem that you all are very well aware of, which is climate change. Here's CO2 for the last 10,000 years. Can you see the end there at the right? Oops, Industrial Revolution. And that's, of course, driving the warming effect from greenhouse gas. And I think everyone knows this, but sunlight comes in, absorbs in the earth, and then when the earth re-irradiates it in the infrared, that's when the greenhouse gas puts it back down towards Earth. So major problems from climate change. And so that's reason number 2. And then the third reason is kind of one that people don't talk about much, which is just it's going to run out at some point. And you don't hear much about peak oil, but that's still kind of out there. Since we invented horizontal drilling and fracking, it's kind of like, we got a long time before we run out, but that's another concern. All right, so world CO2 emissions today are going up. In 2018, they increased by a full 2%. They're going in the wrong direction. All the climate models say, hey, you better get to net zero by 2050 and go deeply carbon negative to 2100 if you want any semblance of a 3 degree Celsius rise, which is thought to be, manageable. But it's currently increasing, mostly oil production, mostly in Asia. So we're going in the wrong direction. So we're not doing great. We're totally fossil fueled. We're increasing CO2. Oh my goodness. Everyone worried yet? Great. Okay, but don't worry, there's hope. We have plenty of energy sources that are low carbon. And here is a plot of them in order. This is how much life cycle emissions of CO2 equivalent are produced per kilowatt hour produced by each of these sources. So here you see coal, biomass, natural gas are very high carbon. These energy sources literally take carbon plus oxygen, combust them together, and form energy and CO2. That's what they do. They must create CO2 to function. Right? Now biomass, you might say, well, that's in this closed cycle. The biomass grows, right? So it's fine? No, because when you burn it, it's much faster to burn than to grow. And so you end up, well, net, you may be pulling out as much as you're putting in. You get a net increase in the concentration of the atmosphere, which is what causes global warming. So you can't have it. So these are very bad. And then you have things that don't use combustion. Solar, geothermal, hydropower, tidal, wind, nuclear. And those are very low carbon because, again, they don't literally take carbon and oxygen combine. The solar photovoltaic effect is light, shoots an electron off and off it goes. Nuclear literally splits heavy atoms to make heat. There's no CO2 involved in those. They're non-zero because these are life cycle, full from construction, mining, to decommissioning, fueling, operation. So you got to go drive trucks around and clean off the solar panels so they have a little bit of carbon emission. Nuclear plant's got a bunch of concrete in it. You got to make that concrete. That's some carbon emissions. So these are life cycle numbers. Anyway, and you'll see the interesting thing. Most people don't know that nuclear is among the lowest carbon forms of energy we know. 60% of Americans think it contributes negatively to climate change. Which drives me crazy because you're splitting atoms. Where's the carbon coming from? So this is a pretty important point. And interestingly, among all of those, it's really unique in that it can run 24 hours a day, and you can put it anywhere. Hydro can run 24 hours a day, but it needs a big geography that's appropriate for it. All the other ones are intermittent, and therefore require huge backup storage. We'll talk about that. I'll speed up, I promise. Fuel dynamics in the US look like this. In the US, carbon emission is going down for one very specific reason, which is that we're replacing coal plants with fracked natural gas plants. Remember on this slide, natural gas is a little bit better than coal from a carbon perspective, but it's extraordinarily high carbon. It's not okay as a bridge fuel or any of these things you may hear. It's absolutely unacceptable. It is much better from an air pollution point of view. It doesn't kill that many people like coal. But from a carbon point of view, it's a no-go. Do not be lulled by natural gas. Well, so what we're doing is we're switching from coal to natural gas. That's going to bring our emissions down a little bit to a completely unacceptable level. You'll see renewables are increasing, and that's going to start helping, but natural gas is increasing faster than renewables. Good old fracking. Fracking makes natural gas stupidly cheap, and a natural gas turbine is like the simplest machine. It's just a big jet engine bolted to the ground, one dude on a throttle. Trivial to operate. You can build a gigawatt for like $1 billion. They're really, really cheap. But high carbon. Okay, moving on. Nuclear power. So nuclear was invented, well no, nuclear was enabled by two women 40 years apart from each other. Marie Curie was the one who isolated something that was discovered earlier to have some energy coming out of it. She coined the word radioactivity and isolated the first radioactive materials, polonium and radium. And she really laid the groundwork for all the nuclear physics discoveries, the nucleus, the structure of the atom. All that stuff came thanks to Marie Curie and her experiments. Nobel Prize, 2 Nobel Prizes. And then 40 years later, there were some experiments that were interpreted by someone named Lisa Meitner. She said, you're interpreting those experiments wrong. That atom didn't absorb the neutron and become a bigger thing. It split the atom. You split the atom. And she was the first to really identify fission, which kicked off this huge chain of events, Manhattan Project and whatnot. Kicked off a chain of events. It's a chain reaction. That's a good one. The second she did that, she just in her head, this always boggles my mind. She's like, geez, so if we split the atom, that means this much mass was converted to energy, and that means, oh my gosh, there's a huge amount of energy that was released. And she came up with a number that was within a 2% of what the real number is, amazingly. And that number is this. And this is the incredible physical fact of nuclear energy. This is how much energy is in a kilogram of each of these energy transfer meters. So 19 kilojoules in a kilogram of sugar, 39 in a thing of fat, 46 in a kilogram of gasoline, 76 million in a kilogram of uranium. This is a mind-boggling amount of energy in a tiny amount of thing. That's because it's nuclear energy instead of chemical energy. And it says log scales are for quitters who can't find enough paper to make their point properly. Of course, if I really was serious, I would bring in a stack of paper that big, but I ride a motorcycle, so. So, of course, 1938, the world is in an interesting place, and the first thing that gets, the implication of this is thought of as a weapon. You can make a crazy weapon if you have that much energy coming out of a small thing. And so indeed, here we are in Seattle. Here's the B reactor in Hanford getting produced. Its job during the Manhattan Project was to take natural uranium from the dirt, throw neutrons at it, turn it into plutonium that you could then put into a nuclear bomb. Of course, that was successful. Here's a very small nuclear explosion test that happened in the 1946 or so. So the weapons development was successful, and this sort of terrible new era of warfare entered the world, and that's the world's first exposure to nuclear technology. Of course, fire is used in weapons, but it was first used as cooking, for cavemen, and so everybody kind of likes it. But this came in as a weapon, and it sure can be used for cooking, but I think a lot of there's a lot of PR elements, and a lot of it has to do with its entrance as a weapon. But anyway, so we'll talk about that more if you want. So after that, right after the war, Congress gave control of the atom and all of the technology to the civilians. It was decided not to make it military. But the first kind of reactors they developed for non-weapons purposes were all specialized military reactors. These were all the places where that much energy in a small amount of fuel is really valuable. Anyone been to Bremerton? There's a bunch of nuclear-powered submarines. Here's the first prototype in Idaho. This is the Seawolf. So 1955, we launched the first nuclear-powered submarine. And right after that, people took submarines up to the North Pole under the ice for the first time. They did a circumnavigation of the entire world, submerged for the first time. All these new submarine capabilities came on because you have 30 years of 100 megawatts in one core. It's just unbelievable energy density. The Air Force wanted a nuclear-powered bomber. That didn't work out, but they spent a lot of money on it. And the Army built a bunch of really tiny, strange reactors in places like Greenland, in an under ice base called Camp Century, Antarctica, Panama Canal, and that was a little truck-mounted reactor that the Army was going to use in forward military positions. So these were the first kind of reactor applications after the weapon. And then we started looking for commercial nuclear power, and the U.S. government and the utilities did this huge series of reactor development programs where they tried out all kinds of wonderful reactors, organic cooled reactors, gas cooled reactors, liquid salt reactors, thorium reactors, you name it. They tried everything, and they really did exotic stuff. And the ones that worked best were the ones like Shippingport, which were water-cooled, water moderated, very similar to the submarine ones. And those, frankly, just worked best. They were pretty forgiving. The other ones they were working okay, kind of, but they had trouble and they needed 5 more years here and there. And so the utilities said, hey, let's just build the one that works. And so we got a bunch of like regular water-cooled reactors. And that's what we now have all over the place. And we'll talk more about these because people have become interested in some of these old concepts. They call them advanced nuclear. It's funny because they were all developed in the 50s, but just to a prototype stage. So there's some interesting capabilities in here, but because they just didn't quite perform as well as the water ones got built. That's the story. And you may have heard conspiracies. They're all wrong. It's that simple. I literally spent like a full month over holiday, like deep diving on this particular historical topic. Wrote it up on whatisnuclear.com. It's an 83-minute read. Okay, it was a great holiday. We also did some pretty exotic civilian stuff. We built a nuclear-powered merchant ship. Imagine all those container ships going around without causing any emissions or having any oil usage or anything. We had one. It was called the Savannah. We also sent a nuclear reactor into space. We've spent lots of little probes into space that are nuclear powered, like Voyager, that thing that's like way out past Pluto that's still transmitting. Where do you think it gets its energy? From a nuclear space battery. The Mars rover the Mars rovers generally have nuclear powered, not reactors, but isotopes that produce a lot of heat, and they power it for very long times. Imagine a battery that you only charge every 300 years, produces 500 watts for a couple hundred years. It's kind of cool. So it's great in space. Anyway, and then the world did go ahead and build a huge fleet of commercial large-scale nuclear power plants, like the one Carl mentioned, which is right there in Richland. There's about 400-ish, a little bit more than 400 commercial power reactors, again producing like 4% of the total energy of the world. Some really good success stories, like in France, where they're highly decarbonized because of their fleet. And then worse stories like in Germany, where they decided to just shut them all down. And we just, if you read the New York Times yesterday, you found out that Japan announced they're going to build 22 full-scale coal plants because they have decided because of what happened at the accident in Fukushima, they just aren't going to they got to shut all their nukes down. But they're literally building coal plants, like today. I can't believe it. But anyway, we'll talk about that. There's a lot to unpack there because of the accident. If you haven't been to electricitymap.org, I think it's .org, you got to go. It's like live data about where electricity is coming from in different places of the world and how much carbon intensity it has. So it doesn't have data for the whole world, but where there's data available, it shows it. And you'll always see that France is super green. It's extremely low carbon, and they break down where they're currently getting their energy from on a day-to-day basis. So you can see France has a vast amount of nuclear power. They built 58 reactors in 12 years, 20 gigawatts per year. Back in the 70s, they did it cheap, they did it quickly, and now they have the most decarbonized the most decarbonized electricity of any European country, except Iceland, which is totally geothermal. That doesn't count because you can't do that everywhere. And then you can see places like Germany where they spent $500 billion on wind and solar, and they're shutting their nukes and leaving their coal on, and they end up having vastly more carbon emissions than France. So there's very clear, large-scale proofs that you can decarbonize very quickly and effectively with nuclear technology. All right, so speaking of nuclear technology, I want to just do a really quick, strobe light version of how reactors work. This will be quick, so bear with me if you know this already. So first, in any energy carrier, the energy has to be put in there somehow, right? So in a plant, photosynthesis rained down on it and built and put some energy in there. If the plant went underground and decayed for millions of years, or however long it takes, it turns into oil, and that's where the energy in oil and coal come from. Nuclear energy was put there by a supernova about 14 billion years ago. Here's a picture of it. It's a different one. There was a supernova. All these neutrons spewed out and piled up on atoms and stored all this energy in atoms, certain atoms. And those atoms then cooled into rocks, and if you go and you can find rocks, and that energy that was put there 14 billion years ago is slowly bubbling out of these rocks. This particular rock has uranium mineral in it. And you can go out with a Geiger counter. Actually, hang on. So I have a uranium mineral in my pocket, I think. That's my tritium. Hang on. Here it is. So this is a little rock that has uranium mineral on it, and it has energy slowly bubbling out of it that's been bubbling out for the last 14 billion years. Now, it's not bubbling out very fast because uranium has a very slow half-life, so I can hold it. It's not really hurting me. It's not hot. I can't turn a turbine with this. But I can use a Geiger counter, like this one, to detect the atoms decaying and giving off their energy. So I don't know if this will be loud enough, but there's a little detector here. And you know, everything's radioactive. Like there's cosmic rays coming down, there's radiation in granite. So we're always bathed in a low amount of radiation everywhere in the world. Some places in the world much higher than others, but we're in a pretty kind of normal average place. So it's clicking a little bit. Can you hear it? Yeah. So then you take the uranium, which is bubbling its energy out, because it was put there by the supernova, bring it close. And there you go. Every click is one particular atom decaying and shooting a bunch of energy out. It's kind of crazy. You can detect a single atom decaying. And there's a lot of them decaying. Turns out there's a whole lot more atoms in there. So anyway, so the energy goes into the rock. Everyone believes me now.
I'll show the internet.
All right, yeah, go ahead. Just flip it to audio. So then you crush, but since the energy is not coming out fast enough, you have to come up with a way to get it to come out faster, because if you want to boil water or do something useful, you need heat. And so you crush the rock up into yellow cake, you put the rock into giant spinning centrifuges, and you enrich it. There's two types of uranium, and you need to separate them, and you just do it by spinning them. Now that you have enriched uranium, you fabricate it into little pellets. They're like there's a sample over here. Little ceramic pellets. You stack those up into these big fuel assemblies, and you take a bunch of assemblies and you put them together in a core like this under a coolant like water. Drop one of the big assembly, core of assemblies, and then it becomes a critical chain reaction. And one atom splits, a neutron goes out, splits another one, and you start releasing that energy from the rock much faster. It becomes very hot. Now you can do something useful like boil water. So here's your hot chain reacting nuclear reactor, and you just put a coolant in and turn a pump on. So the pump pushes the coolant, which is usually water, but can be all sorts of other exotic things. Pushes the heat around, the heat goes into a steam generator, and you just make steam. And the steam goes down this tube into this turbine, which is like a pinwheel. It blows on the turbine. I should bring one. And it spins, it's hooked to a shaft, it goes into a spinning magnet, which goes out to the generator and makes electricity to power, to give us that quality of life that we so appreciate. Now, there's a cooling tower way over here in this tertiary loop. Its job is to take the steam and turn it into water so you can go around the loop again. So this is very detached from, the radiation is in here, the cooling water is here. So this, a lot of people think it's like radioactive smoke. It's actually hot, it's warm water from the river. It has no additional radiation in it whatsoever. So anyway, this is a general power cycle. If you put a coal station in here instead of a chain reacting nuclear reactor, it look pretty similar. A lot of coal plants have big cooling towers like that too. People always assume it's nuclear, I don't know why. Simpsons? Is it? Okay, so then once the atoms have split, you've split all these atoms into little half atoms. You can't get useful energy out of them, but they're still kind of hot. They're still releasing some of their energy. That's the nuclear waste. And nuclear waste is put into these parking lot things. Here's our friend Jim Conca. And this is at Columbia Generating Station. They're put into these huge, those big assemblies are just loaded up into these shielded casks. And you can walk right up to these things and hug them. And you don't want to hug the assembly itself because you'll get a fatal radioactive dose in a couple seconds. But if you put it in this much shielding, you won't. You can go up and hug it. So it's a manageable hazard. It's like putting gasoline in your car. Like you don't hug gasoline, so you don't hug this. So anyway, and here's another example of that energy density. That right there is half of the nuclear waste from 33 years of powering a giant city like Seattle. So over a gigawatt, that's how much waste it makes in 15 years, which really just blows my mind. No other energy source makes that tiny amount of waste. And since it's so small, even though it is very hazardous stuff, since it's so small, you can deal with it. You can deal with it safely. And as far as I'm aware, someone please correct me or look this up, I cannot find a peer-reviewed article that suggests that a single person in the history of the world has been injured, much less killed by commercial stored nuclear waste. Think about that. And everyone knows nuclear waste is like a huge problem, right? But here's fossil killing 8 million people a year through air pollution. 8 million! And here's nuclear waste with Jim Conca walking up to it, giving it a hug. I don't get it. So we'll talk about that Q&A. This is, again, here's the spent nuclear fuel assembly. Once you store it in that cask for, I don't know, 20 years, it cools down. Then you take it for deep geologic disposal, you load it up into a giant copper thing, and then you drop it down one of these holes in a mountain like this repository they just built in Finland. So you can put it into the stable crystalline bedrock type formations and it'll stay out of the biosphere. So you think, okay, it's safe on the parking lot, but what if a meteorite hits it and like disperses that stuff everywhere? And so we say, okay, fair enough, let's put it way down out of harm's way. And so there's a pretty good scientific consensus on this being the solution to nuclear waste. And again, Finland, practical people, said, hey, we got nuclear waste. You guys want to deal with it? And the Finns were like, yeah. And so they built this and did it. Like you can just choose to do that. Of course, in the United States, it's way harder because people basically stonewall you no matter what you want to do. They say it's too dangerous to move. And you're like, well, then don't you want to put it underground? And they're like, no. And you're like, well, is it dangerous? Anyway, you see it's basically a self-defeating argument. So anyway, nuclear waste is a totally scientifically solvable consensus solution, ready to rock, and has never injured anybody, contrary to what you may have heard. Fun fact. All right, I'm sorry if this is taking.
Drop some hostile architecture on us before moving on from that?
Maybe.
You know about the hostile architecture?
Oh, yeah, the one that says, like, don't come here, even though civilization already collapsed.
This is not a memorial
of
some great deed. This is a dangerous place.
Right.
Like, that is such a great script. And then the actual design concepts that they've done for this.
Yeah,
it's so much fun.
There was a lot of money spent on making sure that people 10,000 years from now would be like, oh man, we shouldn't dig whatever is under there up.
Yes.
Meanwhile, we kill 4 million people a year from just burning fossil fuel. And like the asymmetry of that just boggles the mind, in my opinion. Anyway, and then you've got climate change looming. Anyway, okay. So moving forward, where are we at? So we've got a low carbon, low emission, tiny footprint. Not just it's a tiny land footprint. It uses very few materials, very little transportation, very tiny amount of mining. It's like very few deaths per terawatt hour. 24/7 reliable, not geographically dependent. Hooray! But there's problems. It's expensive. There have been some accidents. How many of you can name a nuclear accident? Yell it out. Chernobyl, Fukushima,
SL1,
HCRE3. Anyone? Who can name a hydroelectric dam accident? Banqiao. How many people died? 150,000 people died in 1975. How many people knew that 4 million people died per year from air pollution? Not that many. Okay, you kind of knew. It just drives me crazy that like this dam failed, and I mean natural gas explosions happen all the time, and people are like, oh, 40 people died, like whatever, and Fukushima happens, which killed precisely up to 1 person from radiation, and it's the biggest thing you've ever heard of, and so that's sort of it's like a psychological issue because they don't make HBO miniseries about air pollution. I don't know why. Anyway, and so right now, fracked natural gas is so cheap that we're actually shutting down a lot of our 100 nuclear power plants and replacing them largely and almost invariably with fracked natural gas. That is happening. People want and hope that it will be replaced by wind and solar, but you talk to your utility executive, they're like, does wind and solar run in the middle of the night? And they're like, no, they're like, all right, build a natural gas plant, that's cheap. And off they go, because guess what? Customers demand power even at night. And when it's calm and when it's winter for a long time, and it's those cold, low pressure periods where there's no wind for 10 days every January. You guys like power? Anyway, here's the deaths. A lot of people become pro-nuclear or non-nuclear skeptics after they look up how dangerous the various accidents have been. Like if you go look up the estimated number of deaths caused by Chernobyl, just go look it up, like go find a reputable source. You'll find the World Health Organization and UN have something called UN STEER. And you'll find that here's all the deaths from air pollution, biomass, natural gas, and here's nuclear, including the consensus estimates from a panel of 100 scientists and engineers not just the quick deaths. There were 60 people died of radiation syndrome, firefighters. I mean, tragic deaths. And then up to, and they keep changing exactly the number, but in 2006 they said up to 4,000 people may eventually die from early radiation-induced cancers. Later they came out and said, okay, we don't actually recommend multiplying tiny dose rates by large populations to get big numbers of death. So there's some uncertainty in this, but this uses the 4,000 sort of a high limit. So again, 4,000 people total have died from nuclear, 1 from Fukushima, and 4 million a year from fossil fuel. Why is anyway, I'll stop. I'm being let's talk about cost. So cost, I mean, you have this pretty hazardous radiation inside a thing. You got to put a bunch of shielding around it. You have to have a lot of quality assurance regulations and whatnot. Lots of documentation. It's just expensive. It's sort of, there's some inherently expensive things about it. But this is people don't usually hear. You'll hear people say wind and solar are currently competitive with fossil fuel right now on a levelized cost of electricity basis. People say that, and there's an element of truth to that. It's true if you go out and buy one solar panel on the margin right now. They're being mass produced. The fuel's free. It is really cheap. You can get it and put it in, and it'll be really cheap per kilowatt hour. That's true. But what isn't true is it does not scale. The only reason it's cheap is because there's a massive fossil fuel powered grid backing it up that can come up and down when it goes down. And so if you go look at, okay, let's go to 80% renewables. Here's a study from the National Renewable Energy Lab. These are the renewable folks. And they say, okay, here's the increased cost over baseline. This is the delta when you go out to 80% renewable. And you can see that you get like $20 to $40 per megawatt increase. That's to pay for integration. Your battery storage systems, your massive new transmission lines, your flexible loads that can come on when the wind's blowing. Those things all cost money, and that's how much money. Now, it turns out nuclear is more expensive than natural gas right now by about this much. So if you start asking, what's the cost of energy in a clean energy world where you've gotten rid of fossil fuels, nuclear is already competitive. It isn't competitive right now because natural gas is cheaper. But when you go out there, boom, it's all of a sudden competitive. And we are struggling and trying hard to make reactors that are cheaper and competitive today with natural gas. It's not easy. And I'm sort of starting to argue, like, well, it doesn't matter because natural gas isn't clean and we don't want dirty fuel. So that's the cost argument. And there's also, this is just a thing out of Vox. These are all the billion-dollar plus things that happened in the United States in 2017. $10 billion for wildfires, $200 billion for Hurricane Harvey, $2 billion for central severe weather. These are all weather related. And I'm not going to go and say this one's climate change caused or this one's climate change caused, but I think we all know the consensus is as climate change worsens, these things all kind of get worse and more expensive. And so there's probably some value in spending a little bit more money on things that prevent things like climate change and air pollution. Okay. Thorium. So I have to say I really appreciate that Andrew Yang is the only candidate on the Democratic side who's really outspokenly pro-nuclear anything. And he talks about investing in nuclear to help with the climate change issue. I consider that extremely pragmatic, as you can imagine. And I'm really excited that he's out there saying that stuff. It's really causing a lot of good discussions and bringing, I mean, I think a lot of people in the room are probably here for this reason. So I'm really excited about this. And I actually really considered getting a thorium vanity license plate in Michigan in like 2004, but I didn't do it. I kind of regret it now because it's popular now. Back then, like no one knew about it. So let's talk about it. It's an alternative nuclear fuel. The first reactors used uranium because it has a fissile component in it. Uranium-235 splits readily. So you can take uranium, throw it in a big pile of graphite, and it will become a critical chain reactor. That is the only reason uranium got started first. Thorium only has the other kind of isotope. It's called fertile. It doesn't split when a neutron hits it, but it absorbs the neutron, and the next neutron that comes in will split it. So you have to invest a neutron, and the second one does it. So if you take a pile of thorium and stick it in a pile of graphite, it doesn't go critical. So there was no physical way on Earth in 1942 to make a critical chain reaction from thorium, so we had to use uranium. But After that, we built up enrichment capabilities, and we made plutonium, and we made things that can be the spark that lights a thorium. We made things that can make those neutrons that can be invested in thorium. And so, and there's higher concentrations of thorium, 4 times more in a lot of the crust. So there's more thorium than uranium. And in the really early days, we thought there were like 2,000 tons of uranium on Earth. So everybody said, we gotta breed thorium in order for this to work. That was how we thought it was gonna happen. So a lot of people like started looking into thorium breeders and all that. Early days, but then like I Love Lucy did an episode on uranium prospecting. And it turned out there's like a huge amount more uranium than was expected. And so it was deprioritized, and we just stuck with the uranium. The Navy did the uranium side of stuff. And they did actually throw thorium in that first shipping port reactor, and they bred with it. That was the first time thorium was used. And then in the third pressurized water reactor, Indian Point, started up with the thorium core because the utilities were really interested in the benefits of thorium, mostly that it's more sustainable. But it actually caused a bunch of technical problems. And the second core, they got rid of it. And they said, forget it, just use uranium. We don't want to deal with this. Uranium's working fine. And part of the reason for that is you need to do, as I said, you have to invest a neutron in it. And when you make a reactor that allows you to invest neutrons and then burn them, that's a more complicated reactor in general. It's called a breeder reactor. It has extra features, extra complications. It's just a more complex machine. So as the industry was trying to make reactors for as cheap as possible, and as uranium turned out to be super plentiful, everyone just went off with uranium. And we kind of forgot about thorium for a long time. Until Kirk Sorensen, bless his heart, NASA tech, finds an old book from 1958. It's one of a series of like 10 books that was made for the second Atoms for Peace conference under Eisenhower. And it just has like a list of all these fluid fuel reactors, which are reactors that use solutions of nuclear fuel and other things to make power rather than just flowing a coolant past rods. And they have like pros and cons, and some of the pros are pretty intriguing. He got super into it. He told me at a conference, he's like, I'm going to rebrand nuclear as thorium. And like, no one will know. And at the time I was like, I think they'll figure it out. But I have to say, he's done like an unbelievable PR job. He's gotten tons of people excited about advanced nuclear in general, sort of through thorium, because he's used, by saying, somehow thorium is easier than saying molten salt reactor. And I think it's because it's one word. Because thorium really works well with fluid fuel reactors. It just so happens when you're breeding with thorium, if you have a fluid fuel, you can pull the chemicals out that you need to pull out really easily because it's already a fluid. And fluid fuel reactors can do interesting things like they don't need backup power. If the power goes out because a tsunami rolls in, like happened at Fukushima, you need backup generators in a water-cooled reactor to cool the afterheat when you shut down the reactor. But in a fluid fuel reactor, you don't need it. The fluid will actually just naturally convect and dump its heat without any backup power at all. So you have this extra safety based on the fluid fuel. It doesn't actually have anything to do with the thorium. It just so happens that thorium and fluid fuel are often come together. They don't have to come together. Tommy works on a fluid fuel reactor that uses uranium as the fuel instead of thorium, but it has the same safety benefits. So anyway, you may have heard the story that you can't make bombs out of thorium, and thorium was only not done in the first place because it couldn't make bombs. The military wanted to make bombs. 100% false. I can show you all the documents from the time that say that that's not true at all. It had a lot more to do with the fact that uranium was around and the reactors were stable. The utilities were like, hey, we can make reactors that make bombs. And the US government at the time was like, no, we have enough plutonium from Savannah River and Hanford. We do not need any more. Like, please stop offering to make plutonium. That was really early. That's in the 50s. But anyway, and it does, there are some waste benefits to thorium. It makes fewer of the really long-lived heavy elements, the minor actinides. That's true. So if you look at how much a repository has to handle as a function of years, out to 1 million years, it dips down a little bit earlier. That's true. But you still have to make a full, basically the same kind of long-term geologic repository. It doesn't solve the problem. You still have fission products. They're still very radioactive, and they still are radioactive for a long time. So it doesn't eliminate nuclear waste. You still have to have a repository. And my argument is nuclear waste is an easily solved problem. So let's just solve it, and then we can use whatever reactor for it. So anyway, this is actually a picture of a reactor vessel from a fluid-fueled system that was built at Oak Ridge. I just think it's kind of a great picture. You can make this really simple kind of, it's just a pot with a fluid going around, and it's a lot simpler than a normal reactor. Of course, that's a little tiny one. So if you go to a power reactor, there's a bunch of chemical equipment hooked up to that, so it's not, it can be fairly complicated. So that's the basic thorium story, and again, I'm sure there will be questions on that in the Q&A. I got in trouble with the internet when I made a thorium myths page because I got so sick of hearing stuff that just wasn't quite true. And I was like, that's not quite true. I appreciate that you really like it, but here's some here's the real information. And what's ended up happening, I'm like totally on board with people who love thorium now, because what always happens is they're like, I love thorium, it's so awesome. And I'm like, yeah, check out all these cool things thorium can do in advanced reactors. So if you just map thorium to advanced nuclear technology, it's pretty accurate. Like, it has big safety advantages. It reduces these issues, but doesn't eliminate them. There's potentially some advantages in cost. But anyway, I think thorium is just popular because it's the one word. And so when I hear thorium, I just hear advanced nuclear in general, including thorium. It's sort of a subtlety. I'm sorry I'm taking too long. It's almost over. Advanced reactors, here's like the world's most advanced reactor. It's a hydrogen-powered rocket. Back when we were doing nuclear thermal propulsion, nuclear makes great rockets if you want to go to space. Actually, if you want to go to Mars, like really quickly, nuclear's a good way to go. There are a bunch of reactor designs that don't use water, and they have special abilities. I already mentioned natural safety. No backup power required. There's dozens of reactor types that can do that. There's liquid metal, sodium-cooled reactors, the molten salt, which is, anyway, I won't even belabor that point. Molten salt and liquid metal are different, but who cares? Organic cooled reactors were attempted. Gas cooled reactors, they go to really high temperature. All these things can have this natural safety. You can do a lot more than electricity with some of these advanced reactors. If you go to high temperature, now you have access to, I mentioned electricity is like 40% of our total energy. The rest is process heat. If you want to make steel and concrete or other industrial processes, you need real high temperatures. And right now we burn natural gas to get to those really high temperatures. Some of these advanced reactors can start breaking into that industry, the industrial heat market. There's a lot of people trying to make reactors that are simpler than water-cooled reactors. If you don't need those extra safety systems because your reactor is inherently safe, well, it's cheaper because you don't have to put a bunch of equipment in that's never going to get used, God willing. This has not been demonstrated. Nobody's made a reactor cheaper than a light water reactor, but there's a lot of reason to think it could be done. It still needs work, and that's associated with the economics. These go together. So economics might, if you can get more market, you can get higher thermal efficiency, and you can make your reactor simpler and easier to operate, it should be cheaper. We need to demonstrate that. If people tell you their reactor is definitely cheaper, and you say, where's your prototype? Then don't believe them. They don't really know. The only way you can know is to have a prototype. You can have intelligent guesses and have a good reason to do it, and that's what motivates the creation of a prototype. Less waste, I already said, doesn't really matter, but you can make reactors that, you can reprocess the waste, that's true, and you can get a lot more energy out of the amount of waste, but with how much uranium we know there is, we won't run out of uranium at world scale. If we powered everything in the world with nuclear power, we'd run out of uranium in I think it's like 100 million years at this point, if you use breeder reactors. Actually, no. So you have to use advanced reactors if you want to get it to be the 100 million year range, because you have to get all that energy out of it. So but with current reactors, you can still do probably like 1,000 years-ish, and then you have to transition to the advanced reactors to be truly sustainable on a world scale. So it matters, but not yet. It will matter if we make more than 5% of the world's energy. And then the biggest concern, I've been doing advanced reactor development for the past 15 years, and one thing that's become clear is that when the LWR development people went through and did all this development with Admiral Rickover and the submarines and then like dozens of commercial plants, when you do an advanced reactor, you have to go through all of that stuff again. Not all of it, but a significant amount of it. There's a huge amount of development, supply chain, and understanding physics that was created, and we've kind of lost a lot of our knowledge on a lot of those advanced reactors, so we kind of would have to bootstrap a lot of that to do advanced reactors, and that's a big lift. So you can't just roll in and be like, I got an advanced reactor idea, like, give me money. and I'll build it. Like, it's not like that. You have to do a big development program. And so it's going to be expensive and it's going to take time to do advanced reactors. But not saying we can't do it, but just don't expect it to be a miracle. That's my only message. I kind of am in the field right now, or the mindset right now, where we should build a bunch of traditional nuclear reactors right now in serial, like France did, decarbonize the world, use the proceeds from that to build advanced sustainable reactors. I feel like that's a pretty good pathway. Anyway, so I'm not anti these, I don't want anyone to feel like it's a miracle cure. Ooh, this is my favorite one. Did you guys see Popular Mechanics last weekend? I read this New Yorker article from 1975 about floating reactors in Atlanta. I wrote a blog post about it, and then Popular Mechanics blogged about me blogging about it. Hilarious. This is how the world works. This is what matters most. The ability to deliver any nuclear plant on time, on schedule, is what the utilities and customers care about absolutely the most. They don't really care what technology is. They just want one that isn't going to be a $12 billion, 10-year thing. They just want it now. And if you look at the difference in a good and poorly run project, it dwarfs the difference you can get from going to an advanced reactor, unless somehow the advanced reactor makes delivery mechanism really easy. France and Korea standardized big reactors, built a ton of them, work great. Like, that's a proven model. If you want to do it again, if you want to decarbonize, like right now, pick a reactor, build a bunch of them, decarbonize now. So you'll hear about small modular reactors. That's kind of a step towards that. This is a good way to start scaling up to large modular reactors. We really need these if you want to build, if you want to decarbonize all of that fossil fuel. And if you want to get crazy and talk about reactor assembly lines, the Westinghouse formed a joint venture. They built a assembly line of giant nuclear reactors in Jacksonville, Florida. This is 1975. It got approved by the NRC, and they could produce 4 giant gigawatt scale pressurized water reactors per year, and then they just float them off to their site on a barge. And it's like economy of mass production meets economy of scale. It's the craziest and wackiest idea, but it's one of those things when you first hear about it, you're like, that's crazy and terrible. But the more you think about it, the better it gets. This is my current favorite idea in terms of decarbonizing super rapidly. And again, it doesn't matter exactly what reactor you put on. You probably do a light water reactor because those are the ones that we have a full supply chain regulatory infrastructure for. All right, I'm going to stop talking. Nuclear energy is great. Let us in. We want to help fight climate change. Let's ask questions.
So for a timing note, this library closes at 8, right? So I think we can stay until 7:30. If you have to leave, we're not offended. Nick, as always, has a wealth of information, and we wanted to drink it in, so I didn't cut him off. And if you wanna, anyone who's meaner than that guy, go ahead and tap next to that and block him, unless his name's Ed File.
Oh, I like it.
Yeah, we like him. He's a little mean sometimes.
Yeah, but we can take it.
Yeah, we can take it.
So there's a question there?
Oh, is there? Is there a new one?
No, we can just answer. I'll just answer your question first.
These are kind of silly questions, but I have 2 questions. One is you showed a slide with the United States using their energy, and Norway was to the far right and they're small.
Why are they way up?
Why are they using that much energy? And then the second question is if you swallowed that rock, would it kill you?
Oh, no. Well, I wouldn't, if you crush that rock up and swallow it, it still wouldn't kill me, but those are alpha particles coming off, so it's an ingestion hazard. Like, you don't really want to eat uranium. Like, it would not be recommended. I would probably not crush that rock up and eat it.
But this is
So you would die?
I don't think I would die because it passes pretty quickly, but
Yeah, because this is an oxide, so it has
it's not gonna absorb it.
it has a biological half-life of about 3 days. And when you hear people screaming about half-life, you have to think about both of those things, biological and physical half-life.
Yeah, right. So anyway, yeah, I mean, and don't get me wrong, there are radioactive things that are super hazardous for sure. And I mean, you've heard of people getting poisoned with certain polonium or whatever, lead, whatever it was. But anyway, it's kind of a thing where it's like, the world is radioactive to a degree. At low levels, it's fine. At high levels, it's dangerous. It's just like fire. Like, if you go step into a fire, like, you're gonna get maimed and killed. But this is a little bit warm, just like it's a little bit radioactive. It's an interesting sort of close analogy. Your other question was
Norway.
That's mostly because it's really cold and they have a bunch of energy sources. They just burn through a lot of energy. They have a lot of pretty cheap, plentiful energy, and it's really cold. So
They
a lot
don't
of
have nuclear.
Does Norway have a nuclear plant? So Sweden and Finland have a lot of nuclear plants. I can't remember if Norway does. I have to go to electricity map.
Norway has a lot of natural
Norway has
gas.
a lot
Coal and gas.
Yeah, that sounds right. Yeah.
Cool. Here, let's go front.
Can you help us, what is your thought about the best way to go? We have a lot of light water reactors around the country now.
Yeah.
What do you think is the most fruitful way to get off ground zero here and move forward?
Oh, for new types of reactors?
Yes.
There's a very clear path forward. It's exactly what was done with light water reactors in the first place. You first have like some R&D in various companies figuring out which reactors are going to be the most interesting. They run reactor experiments kind of on their own dime, a little bit of government help here and there. And then somebody decides to build a small prototype reactor, 10 megawatts. And if it works really well, which it has to do first, if it works well and it operates nicely, then a consortium of utilities, roughly 10, needs to come together and say, all right, we're willing, we like the characteristics of that reactor, that thing load follows, it's cheap enough, whatever, and we're gonna, as a consortium of utilities, we're gonna buy 3 of them, and then in growing scale. And then assuming that goes well, everybody goes and buys them. But that's how it was done with the light water reactor. Right after shipping port, a consortium of utilities came together and they built the first pressurized water reactor. It worked great. Yankee Road was an incredible reactor. And then after that, it just took off. Everybody bought it.
Does anyone know of a consortium of utilities we could find? Like Energy Northwest has 27 utilities under its purview, and Seattle City Light, or your city government, is one of those. So
Yes.
talk to your city council member about supporting Seattle City Light's management of nuclear energy. I think there are 2 in the back.
I've never heard the term brown coal used before.
Brown coal or lignite. Coal at different depths and different ages has different lengths of carbon, and the different lengths and purity of carbon means that it either burns cleaner or dirtier. Some of the most accessible coal in Germany is this brown coal. It's very impure. It kicks up a lot of particulates. It kicks up a lot of CO2. It's really bad stuff.
I was just going to say Norway is 97% hydro.
Hydro. Yep.
There you go.
Why are they decommissioning old nuclear plants now?
They're the main, I mean, the ones that are, so what's happening, we have regulated and deregulated energy markets in the United States. And the ones that are deregulated just means whoever can generate electricity cheapest is going to win out. And that's a lot of the Midwest and the East. And so what's happening is, because natural gas is so ridiculously cheap because of fracking and horizontal drilling, people can run natural gas plants for like way less than they can run their nuclear plants. Now nuclear, to operate, it's not cheap, but it's not overly expensive. The only thing that's happened is that because natural gas got so cheap, the electricity price went down with it, and so the revenue going to the nuclear plant is way less, and so they just can't pay the operating bill. And so we're saying, well, natural gas is cheap right now. Who cares that it's a fossil fuel, it's super high carbon? Let's just kill this like continuous energy gigawatt scale nuclear plant because we can't think past 3 years of operation.
We could
Like,
just
that's
turn them.
literally the reason.
We could turn them back on, couldn't we?
Not after you decommission it. Yeah.
Yeah. That's
And the whole staff leaves. Yeah, it's kind of this great tragedy in the United States because of that going on right now.
There's a little more detail, is that when we're fracking, we're pushing, the fracking fluid into a rock formation. You get a big chemical mixture when that comes up. That is part oil and part gas.
Yeah.
And the price of oil per barrel is somewhere north of $60, I think. It's very, very profitable to make oil. And so they have this natural gas that you can't burn off, or you're looking for a market where you want to sell it, really.
Yeah. The easiest, the trivial solution, from a policy point of view, but of course it'll never happen, is a carbon tax. You put a carbon tax in, all of a sudden the nuclear electricity is infinitely more valuable. The natural gas electricity is terribly more expensive, and there you go. You want less carbon, put a market price on carbon, and it'll just happen. Otherwise, people are going to game the system. Natural gas is going to say, we're the best friends with renewables, like lock us in, and like that's exactly. And people are cool with it. Like, yeah, whatever, we're fine with natural gas as a bridge fuel, even though it's increasing more rapidly than renewables and taking us to like an infinite lock-in of a high carbon future. So like, someone needs to figure out how to get politically something like a carbon tax through. Yeah.
I'm curious about the liquid salt reactors. Isn't it the problem that there's a lot of, it's very corrosive, and so you have plumbing and materials issues?
So that, they were worried about that in 1960 when they built the first molten salt reactors. Actually, late 50s they built the first one, and they did this huge development program related to the aircraft program. Actually, it was molten salts were developed for the Air Force, believe it or not. And they went through and studied all sorts of salts and all sorts of chemistry control and all sorts of metals, and they found a combination that was appropriate for that situation. Now they ran the molten salt reactor experiment for a couple of years, and they ran really well. They dealt with the corrosion issues. They did run into one problem with an embrittlement of one of the metals, and then they ran another program to figure out how to solve that particular problem. But they never really demonstrated that they had solved it. Like we think it's been solved, but you have to run another reactor to prove it. But the corrosion issue is basically you can deal with it by choosing your materials right and doing chemistry control, and then it's an operable system. The one that they ran at Oak Ridge, Tennessee, ran really well.
The related question is simply because it seems like the easiest way to cool it in my mind is to simply have a goblet with the liquid in it, and then just rotate the goblet so that you've dispersed everything into a greater surface area. And then you could have it to the default position with no power, assuming that there's a blackout or whatever.
Yeah, it like stops spinning or something.
Would just be the thing, so that it falls into a greater surface area.
That's certainly one of the elements of a lot of the molten salt designs, is that they have a freeze plug and it melts if it gets too hot, and it goes out into a big tray that then has passive cooling channels to the ambient atmosphere, one way or the other. Other people just say, just stick a heat exchanger in it. That's going to be way simpler. A heat exchanger that then has a pathway to the atmosphere. That, from an engineering point of view, is probably simpler. Those freeze plugs take 10 minutes to freeze or unfreeze, so they're kind of.
And a real important part of this is the moderator. Nick thankfully didn't get too much into the tech, but there is something like an air-fuel mixture. You know about this with your gas cars. If you have the wrong mixture of neutrons and the barriers in between, it's like having the wrong air-fuel mixture, and it just stops. It does have latent heat, but the reaction will stop. You just have to, as you say, tilt it, and that reaction could stop.
Yeah. Every reactor pretty much, Fukushima shut down perfectly. The control rods went all in, and it was just that latent heat that was the problem. Turns out it goes down to 7% of full power, but 7% of a gigawatt is 70 billion watts. So
it's the latent heat, heating up the fuel elements, breaking the cladding, cracking the water into hydrogen, and the hydrogen below.
So anyway, decay is a big.
You'll go, by the way, we're streaming on yestv.org. You'll go see another video on there all about Fukushima.
What's the global market for Thorium? You highlighted India and China as a prevalent location. Do we have the sources internal to our country to use it as a resource themselves?
Yeah. We could certainly find enough thorium if we had the breeder reactors to breed it up and then use it. There's enough thorium resources in the United States to run the country for hundreds or thousands of years. The thing that's unique about India and China is that they have like no uranium and tons of thorium, and so they have expressed a lot of interest in it specifically for like energy independence purposes. So that's kind of why I highlighted those two. But it's pretty broadly distributed. It's kind of, you can find it all over the place, and there's quite a bit of it.
Be in the back.
Actually, first learned about breeder reactors, reading about David Hahn, the nuclear Boy Scout. And I guess my question is, what would be done to like prevent that?
Well, David Hahn actually broke the law. So the question was about David Hahn, and he bred fissile material and bred very hot material. He was discovered very quickly. This stuff screams. It's really hard to contain. It's really hard to hide. He did actually have to steal by misrepresenting himself. He stole some of the materials he got. He broke open, I don't know how many fire detectors.
Must have
And-
been a lot.
yeah, and you can't find those with MREC in them. It's really hard to find fire detectors with a nuclear element in them anymore, a nuclear source.
And let me add just a little more generally. So nuclear weapons proliferation is something that people are concerned about, right? So like if you have a bunch of nuclear reactors, does that mean you're going to have a lot more nuclear weapons? The technologies have some overlap. The enrichment is similar. They're both nuclear chain reactions. But one thing I'll point out is like the CIA has a list of all the countries in the world that have the technical know-how to build nuclear bombs. And it's like 36 countries, and it's like the biggest, most militarily powerful countries. Pretty much, the cat's out of the bag. Like people know how to make nuclear bombs. And little known fact, the United States for 20 years was buying Soviet nuclear bombs, blending them down and putting them in nuclear reactors and making electricity out of them. So the nuclear reactors were literally taking the atoms that were pointed at them as weapons and using them to power those exact cities. So nuclear reactors are one of the only ways that you can actually get rid of a nuclear weapon. And increasing nuclear reactors, there's dozens of examples where people got nuclear weapons without any nuclear reactors at all. So there's some relation, but getting rid of nuclear reactors will in no way get rid of nuclear weapons. And so it's not a great argument to just not use nuclear power.
Bunch of questions. I forget who was first. I think there's two in the back. Go ahead.
Yeah, I have, I think, probably a fairly elementary energy question.
That's fine.
You had mentioned one of the arguments against solar and wind power being you get into these stretches in January where there's wind.
Yeah.
At night there's no sun. Are you able to get around that by storing energy in the grid or in batteries?
Oh yeah, I mean, there's at least 3 awesome ways to do energy storage. I mean, pumped hydro is the easiest one, and that's the vast majority of the world's energy storage. Is you at a dam, you just run the motor and pump the water back up the dam when you have extra energy, and then it comes coming right back down. So that's one way you can do it if you have dams. Batteries you can also build, but they're quite expensive. They take a lot of energy to manufacture. You have to recycle them you're rebuilding them with toxic chemicals every couple of years. So the overall footprint of them is pretty large, and you get into a situation with something called the energy return on investment, which is just how much energy you get out of the energy system versus how much it took to create the energy system in the first place. And as you build more and more storage, that number goes down and down and down because you're building all this non-productive stuff. And you get into a point where it's just like too low to sustain industrialized civilization. So yeah, you can store energy, but it's a lot harder than you might think. And I'm very much in support of wind and solar where it makes sense, which is a lot of places. I mean, the Southwest and like the Tornado Alley for wind, like that. We need to be doing that. Plus, I mean, we need to have like 10 times more wind, 10 times more solar, and 10 times more nuclear. Like that's where we're at. So everybody has. You don't have to be anti this or that, but the main point I'm making is that as you scale to high penetrations of intermittent energy sources, you run into huge costs in grid integration, which is this energy storage backing it up with whatever and load following and all that stuff just gets really expensive.
I think one time you calculated how large the battery for Seattle would have to be.
Yeah. Yeah, it's just imagine like 50,000 Columbia Tower skyscrapers full of lithium-ion batteries for the United States. It's around that.
I think there was one more in the back before I get to you.
Thank you.
I was just wondering about the next generation nuclear plants that are safe. Do we have physics problems left to solve, or is it just engineering?
It's mostly engineering and material science, which is kind of in the middle of physics and engineering. There's certainly some material questions that need to be solved by putting materials in reactors and irradiating them, make sure they perform okay. But really, it's not even. It's engineering and it's delivery mechanism. Like we need to know how to do really complex, large nuclear projects on time, on schedule. So and that again has only ever been shown to work if you just do one and you do a lot of them. And so the challenge is finding a consensus. There's dozens of advanced reactor companies now all saying theirs is the best.
So was there one more on the back right? Yeah.
Do you see any potential, technologies in the pipeline that might make nuclear competitive with natural gas in the absence of regulatory incentives?
Let's see. So if we could get better at making nuclear reactors load follow, that would be a huge thing. One thing that natural gas plants do that nuclear plants don't do that well is ramp up and down quickly. And so if someone can come up with some relatively cheap way to hook something that can do that onto a nuclear plant, it could be a thermal energy storage is what a lot of companies are talking about, like a solar thermal plant, but charged by the nuclear reactor. So if you can get a cost-effective thing like that, the utilities would just love it, because they're out there desperately seeking a zero energy, low emission resource I said that wrong. A zero emission, load following resource. It's a unicorn right now, and the utilities are seeking it. So if nuclear could kind of swoop in and be like, hey, maybe it's a small modular reactor that has a really good load follow capability, that might excite the utilities. But really, natural gas is like extraordinarily hard to beat on capital and on fuel costs. So I don't think it's going to be easy.
This may be apocryphal or maybe false, or it's certainly an old saying. Bill Gates is supposed to have said, at one point in time, this may be decades old now, that if you took all the batteries in the world and charged them up fully, ask the question, how long will the charge on those last if you load those batteries to run the Earth's electricity system? He calculated about 10 seconds.
Yeah, that sounds about right. And so the implication is you have to build vastly more batteries than have ever been known to man. And that's what people are talking about in terms of dealing with the inefficiency of the world's favorite energy sources, wind and solar. Which everybody loves. They have like 90% of people.
So one thing I was going to say is that any battery-based technologies then compete with like cars. Like you can't have electric cars and grid storage unless you make the grid storage the car in the parking lot.
Yeah, but you can.
Because they compete for the same resource, which is lithium or whatever materials you're using, and construct like your scale process, whatever you're doing to build it, they compete directly. And then the second question, which was the actual question, was
you guys are doing fine.
The second question was, are there any reactor technologies that are non-proliferative? In other words, the material, like what you're using for fuel, can't become weapons grade.
Fusion? Without fission, it'd be hard. Although thermonuclear bombs are fusion bombs too, so you need a bunch of tritium and deuterium. So actually, no, there really isn't. Like,
and if you had a fusion reactor, as soon as you get some uranium close to it, you've got weapons material.
Yeah, and again, a lot of people want to say that their reactor can't be used to make bombs, and some people will go jump through lots of hoops to be like, well, it'd be really hard to make a bomb out of this reactor. And in some cases, there's technical reasons behind that. But the statement I can pretty confidently say is if you are the owner operator of a nuclear reactor of any kind, you can go in there and throw some uranium-238 in there, and if there's neutrons, you can make plutonium. And if you have plutonium in a pure enough form and you can get it out quickly, you can assemble a nuclear weapon. But it's much, much easier to not have a nuclear reactor, enrich it in a mountain, enrich uranium, naturally just take uranium, enrich it, and then you can make a nuclear weapon. That's way, way easier than secretly building a nuclear reactor.
And a really quick comment on the batteries. Fortunately, things like pumped hydro and new battery chemistries are not going to be good for cars. Vanadium flow batteries, not really good for cars, and you can't get a Gordon Butte pumped hydro to run your car, which, by the way, is the name of a battery project that Seattle City Light should be investing in. So.
I had a few questions. One was you started off with the graph that showed kind of what percentage nuclear is currently supplying for energy.
Yeah.
And you said it included multiple types of energy. What level of replacement could you realistically expect nuclear to cover?
So the fastest we've ever built nuclear as a world is 20 gigawatts per year. We did that in the mid-'80s. France was building a bunch of plants. So it really you could go faster than that. That's fast. No one's decarbonized faster than people have done with nuclear. There's some great graphs that show how rapidly different countries have been able to decarbonize. And when in the 70s and 80s, when people were building a lot of nuclear plants, that's the fastest anyone's ever gone. So if you can somehow get back to the days where we build nuclear plants, regularly and quickly, then it would be the fastest way, basically known, to decarbonize the whole system.
And I want to riff on that a little bit. Is the kind of work that you do and you're hoping to do more of in the future, does that compete with the photovoltaics and the wind and the hydro? does it necessarily mean that if we scale up nuclear, we can't do anything else?
Oh, no, I mean, again, like, for solar and air conditioning go perfectly together, like, well together. Like, it's always really hot when the sun is out, and like, so what better thing than solar to power your air conditioners during the day?
But even the build out.
Yeah, I mean, the thing that's hard is if you do build a vast amount of renewables, you have to build in a load following capability that is just dramatically gigantic, whatever that may be. So when you choose to go huge on intermittent renewables, you are setting your, so it makes it harder, I would argue. If you just, and some people would argue this, and I don't want to come off as like only the pro-nuclear guy, but if you were to just build nuclear plants and then give them enough load following to handle the demand, that would be a sort of simpler and easier and lower footprint system than building a vast amount of wind and solar. They aren't in direct competition, but it is,
Yeah.
we don't need to
Yeah.
pick up the burden of intermittency.
I would walk us back and say, well, we would still need to reach the peaks and troughs of nuclear,
Yeah, for sure.
and we could charge our batteries on both ends with renewables in the day, with solar in the day, with nuclear at night.
Yeah.
Oh,
Sorry,
yeah, go
I can, you can go first, I have several, so it's fine.
So when you talk about load following, something that I read about molten salt reactors, which may or may not be true, I'm not sure, is that if you cool them faster, the salts contract and thus increase the reaction.
Yeah,
So
that's.
would that be?
Oh yeah, I mean, any nuclear reactor will load follow to a degree because they all have what you're saying is called a negative power coefficient of reactivity, is a great name for it. And that happens in boiling water reactors, light water reactors. It's all the same thing. If the water density changes, if it cools down, the reaction heats up. And same with molten salt, same with liquid metal. And so every reactor can load follow to a degree. The reason we don't, it's more that it's economically.
Yeah.
In practice, it's bad for the economics because a nuclear plant, because its fuel is effectively free. You load a nuclear reactor with fuel for 2 years, and that's it. Like that loading will last for 2 years. So the fuel is a very low percentage of the cost. So the high percentage of the cost is operation and maintenance. So if you're not generating 100% of your capacity, which is your pipe of dollar bills coming into the building because of electricity sales, if you turn that pipe down, you lose out economically. So nuclear plants, by their nature of having that much energy density, choose to always have the pipe on. They can physically load follow, but they lose money. They lose more money. And if you load follow really quickly, you do get into concerns about thermal gradients and shocking systems and causing bends and stuff like that. So there are also limits on how fast you can change. But a submarine reactor can reactor can load follow real fast in a military scenario.
Okay, one more from you.
Yeah, so in the second graph, when you're showing like the different, I guess, types of energy and the carbon emissions,
Yeah.
I felt like the
Yeah, I
fossil
love that
fuels really kind of skewed, kind of how you would compare the different renewables.
You're talking, because they're all like, so, yeah.
Yeah, so I was
Well,
curious,
that's a
how
good point.
significant is the drop off, for example, between like the
Like solar. All right, this isn't going fast
There-
enough. So that's a great question, and I sort of have like a binary, I draw the line here. These are high carbon and these are low carbon. This is 48 and that's 11, so it's a factor of 5 versus a factor of 10 here. And so once you get down to this point, I mean, this is in the current mix of energy, so it takes a lot of carbon to manufacture and clean a large solar system, or a large solar energy system. But if you were to go 80% renewable and you now have a bunch of electric trucks driving around, electric manufacturing facilities, this would go down proportionally. So if you go to any of these at high fraction, all of these will go down because it's all just the life cycle. Whereas if you do these, it stays high because the combustion is part of the way it makes energy. So I kind of just say low carbon, high carbon, and like that's it. If that makes sense.
In the back, yeah. Oh, there's, let's see, I forget who was first.
I'll wait as well.
Okay, go ahead.
So, the way government works, carrots are often an easier sell than sticks.
Yeah.
In terms of regulation.
Sure.
What carrots can you think of that probably have the biggest potential to move this forward?
Brilliant, challenging question. I'm not sure I have a good answer. I mean, we will give you a world that's livable in 50 years. I mean, that's not a great, no one thinks that way, right?
Well, I mean,
So,
like a lot of the decarbonization skeptics I encounter have a lot of economic concerns about.
Sure.
They don't want to dampen economic growth for the sake of decarbonization.
Yeah.
But if it was a matter of pouring investment into a certain area, I'm thinking that might be able to allay some of their.
Yeah, I mean, right now there's a lot of like philanthropists, billionaires funding a lot of work in advanced nuclear. Like I work for it's a private, for-profit company, but we're funded by billionaires, and the reason is they want to help the world solve the energy crisis, and that's a carrot from their perspective. But from the customer's perspective, like it's not really. You really just would have to say, yeah, I don't know. I can't think of a good carrot.
In terms of public,
about that.
yeah, in terms of public policy, there's this, the bare minimum. Government is spending money to increase health outcomes, so it reduces emphysema, it reduces healthcare costs. There's one carrot, and the mechanism for delivering that to producers would be something like a zero energy credit. Instead of a renewable energy credit, we have a zero emissions credit.
I didn't say.
And that's going to benefit those things like in Indiana, Ohio, and Pennsylvania to keep those plants in operation when they would be competing with gas. And then I like the analogy of the carrot and the stick. So you need to have a little bit of a stick to make the carrot go on. We have taxes, but wouldn't it be much nicer if we also had a little bit of stop polluting so much, so cut down your coal burning.
And carrots make it easier to sell the sticks in any case.
Right. One more in the back.
Yeah, my question was kind of similar, but I guess I'll try to rephrase it. Do you think there's any sort of regulatory issues that are maybe slowing down nuclear, making it more expensive, that are?
Well, I mean, yes and no. There's a lot of people will say like, oh, the NRC is like way too constraining, and that's why we can't build anything. That's not really that true. The NRC is attempting to modernize the way they do regulations and things. And there's engineering development issues that are holding up advanced nuclear way more than regulations at the moment. No one's really ready to go. Very few people are ready to submit a full design in detail to the regulatory commissions. On the other hand, and a lot of the regulations that were made for nuclear were because of certain incidents that happened, and it was appropriate to regulate more to make those things so they wouldn't happen. But there's sort of an argument that maybe we went a little too far. Like there used to be 100 reg guides, they're called, and now there's like 4,000. And it just has become, and the quality assurance requirements on these things, like when you run a wire in a nuclear plant, like it's tagged, you know what factory that wire came from, where the ore that went into the wire came from. And nobody's ever really shown that actually improves reliability, even though it costs like infinity dollars to actually do that. So one thing that might be interesting is to try to do something to say like, let's use stuff from Home Depot but make it more redundant. And if we can prove that that's safer or equivalently safe, that might be an interesting way to help sort of alleviate some of the regulatory burden. It's a really good question, and it's really nuanced, because I don't want to just say like, yeah, forget about regulations, that's not appropriate. But on the other hand, like, again, very few people are dying or have died from nuclear. So the hazards, I think, are asymmetrically understood. And the public really is the regulator. Like, our belief of how dangerous nuclear is what is reflected by the regulator. And so if we can convince people to want nuclear and think it's safe, think it's as safe as it actually is, that would help streamline things just through interventions.
3 last questions. There's one over here. In the front, yeah.
Really quick, I thought, maybe you've heard this, for a stick, carbon dividend on embodied or imported carbon.
I like that. Like you distribute it evenly to everybody.
Yeah. So it's not a tax, it's a redistribution.
I like that.
And so what you're doing with your company is focusing on just trying to make a small light water reactor mass producible.
That's hilarious. Like if I were in charge of my company, maybe that's what we would do. But no, we're not doing that at all. We're building 2 very advanced, high-tech. We're building types of fairly large reactors to do. There's a molten salt reactor that Tommy mostly works on, and there's a sodium metal cooled reactor called the traveling wave reactor that has a lot of the benefits listed on that advanced reactor page. Less waste, better safety, hopefully simpler, hopefully cheaper. And we're trying to deploy those reactors in markets. We were attempting to deploy it in the traveling wave one in China, but the Trump administration Department of Energy cut us off for trade war reasons. So and we're in a real awkward place politically, so I'm really glad Andrew Yang's out there seeing good news.
Do you think that the best way forward would be get something done like really well?
Very personally, and like I may try to convince my opponent of this, but like just me personally, from my research, it appears that the best thing to do right now would be to try to start mass producing a relatively straightforward reactor as soon as possible, like a light water reactor, and then use that to bootstrap the nuclear industry, the nuclear supply chain, relearn how to deploy nuclear installations, scale it up, and then, as appropriate, deploy advanced reactors if and when needed.
This is exactly the pitch that the American Nuclear Society made at the recent convention.
Yeah. There's sort of a consensus on this, to a degree.
I've heard it said that a lot of the increase in CO2 emissions is due to people in really poor areas of the world, construction of coal plants, and coal being is, from what I understand, the fastest growing form of energy in the world. And would you care to comment about how nuclear could maybe help us with that?
Yeah, so the only way, if you're in, so India and China are huge and increasing energy powerhouses, and they have big and thriving nuclear industries, and so in those two places you can expect a lot of nuclear reactors to kind of help displace the coal plants. In places that don't have a nuclear industry at all, it's harder to stand up a nuclear. You have to get a regulator, and the United Arab Emirates just did it, and they have 4 big reactors now. One's going to turn on hopefully this quarter, but that's harder to do in all countries quickly. So so the crazy way you do it, there's these things called power ships that Turkey runs. It's a giant ship with a bunch of gas turbines on it, and it rolls up, and you run a pipeline out to it, and you throw an electric line back, and it produces it. And you could do that with a nuclear plant if you could get people to accept floating nuclear power plants, which is kind of crazy.
Sorry, there's one last one, and we're going to be pushed outside at this point, so go ahead.
What do you think of the potential of fusion, and should we be investing more in that, or is this enough?
So I actually got into nuclear specifically because of fusion, and I got distracted by advanced fission along the way for the last 15 years. I am a fan of fusion. I kind of came to the conclusion that there's a inverted pyramid of technology. There's like idea, physical viability, engineering viability, commercial viability, and each step is much harder. They're at the physical viability step. It's not impossible. There's a $500 million per year company down in California working on it. There's one in town called Helion, and there's one in Canada. So people are putting good money into it, lots of investment, and I encourage that and support it, and I hope that comes through. Once you prove the physical viability, then you have to see if it's commercially viable, which it may not be at all. They're extraordinarily complicated, expensive machines. And then after that, so anyway, I am not holding my breath for it, but I support it, if that makes sense.
So I'm going to say thank you all very much for coming.
And last shout out for Andrew Yang again. His campaign is really
Yang, there you go. I'm sure Nick might be able to hang out upstairs near the entrance before they kick us out. There's all sorts of literature here from the Seattle Friends of Fission. We are your local grassroots nuclear advocacy organization. We would like you to talk to your state representatives, your state senators, and your city council about supporting nuclear development.
And your friends.
Yes. Oh, of course your friends, but
That's the most important.
Yeah. Tell your friends to visit whatisnuclear.com.
And then where will we find this?
This will be on yestv.org, on the Andrew Yang Seattle and Washington Facebook pages, on the Seattle Friends of Fission page, on dlive.tv/thorium, on a bunch of channels.
Oh man,
Thank you.
I hope I talked enough about thorium.
Yes, you did. I have like 2 followers there.
Yeah, you had
All right, I'll try.
Hey there.
Okay. Now this camera, yeah. Am I? Yeah, get all the lights off.